So I don't know, by the way, Brian, if you want to say a few words about the exercises,
Okay.
just in
I'll do that.
of encouragement for people.
Yeah.
Great. So I just call people back in. So.
Okay.
A couple more introductions. So who is another one of the organizers, is here. So, and Conrad, who wasn't here when I did introduction before. All right.
Okay. So first, I should mention. So there are these exercises in my notes, and so if you don't feel like tagging along with a project and all this stuff is totally new to you, then you might wish to just have fun doing the exercises. I hope that most of them are intended to be straightforward. Some of them are intended to be impossible. But anyway, but this is Bryden's responsibility to deal with. Anyway, okay. But they're kind of interspersed throughout the notes, so you can look there, and there's some link to them on some web page somewhere. Okay. Anyway, all right. So last lecture we introduced these affine algebras and the corresponding sort of geometric spaces for which we defined a canonical topology, which we need to sort of improve upon. And in order to do that, we need to identify an interesting class of open subsets with respect to this canonical topology. And this is going to involve defining for affinoid algebras certain analogs of localization operations from algebraic geometry. So in the algebraic situation, if I give you some ring, you can invert a multiplicative set, okay? And particularly inverting one element those are the basic, the basic open affines in spec A, and these are the things that you sort of put together to sort of build a structure sheaf and so forth. In this non-Archimedean situation, the analog of that, there are going to be several different flavors of these localization processes, and these will correspond to certain kinds of interesting open subsets of the space. And one interesting thing, and in order to define them in the most efficient way for present purposes, we're going to need a certain generalization of Tate algebras. But before I do that, let me just say something that you can sort of keep in mind as I'm kind of babbling for the next page or two, which is we're going to try to construct this sort of interesting class of open sets, and in particular construct a structure sheaf out of the functions on those sets before, in some sense, simultaneously with building the right topology. And so we want to have some way of characterizing the ring of functions that should be defined on these open sets by some kind of mapping property before we have the structure sheaf on this space. So the way in which we're going to eventually build some kind of a space with a structure sheaf is not going to be quite in the same linear fashion that happens in the case of usual spec of a ring. But anyway, we'll sort of see how it goes. So to define the correct open subsets, these are the basic construction that we need to get started. So generalized Tate algebra is the following. I give you a Banach algebra. We're going to be interested in the case of an affinoid algebra with a choice of norm. All right? There could be a zillion of them, zillion choices of norms. And, well, I just consider a similar thing, bracket some variables, power series over the coefficient ring, so the coefficients tend to 0 in this norm. Again, remember, this norm may not be multiplicative. Okay? And well associated to that, we have a corresponding Gauss norm, just the max or the norms of the coefficients. Now, of course, in the aphanoid case, there's no canonical norm, but any two choices are equivalent to each other. And so we just observe that if I change this norm by a bounded amount, the Gauss norm also changes by a bounded amount. Okay? And in particular, it's hardly surprising, if we start with an aphanoid algebra, what this corresponds to is putting together the y's and the x's and killing off those same relations in the y's. To verify this isomorphism, you just use the universal property of Tate algebras to give maps in both directions, roughly speaking. In any event, so this produces new aphanoid algebras out of old ones. And now what we want to do is use this to construct some interesting classes of sort of analogs of localization. So we're going to use this to define certain kinds of localizations of A equals a K aphanoid. Now, I should say that what I'm about to do is in some sense the wrong approach. That the right approach would be to develop an elegant theory of completed tensor products and completed algebraic localizations. But we only have a short amount of time here, so I'm going to sort of take a slightly more direct route. So the way I'm about to do something is perhaps not the right way, but that's okay. Okay, so first we're going to introduce what we're going to call Laurent domains. So let's fix A1. So let's say A is K aphanoid. And we have A1 through AN in A, and A1 prime through AM prime in A. And now what I want to do, intuitively, what I would like to think about is a set of points in M of A with the property that the first few guys are bounded above by 1, and the last few guys are bounded below by 1. Okay? So I want to think about, so I might write this more succinctly as the set of points in M of A where A1 is less or equal 1, AN less or equal 1, A1 prime greater or equal 1, AM prime greater or equal 1. This is not to be confused with the norm of the element in the ring. I mean, it's a pointwise condition is what I mean. It really means this, but this takes less time to write and therefore is better. Anyway, so these are we want to consider a locus cut out by this kind of simultaneous class of conditions. So this is some subset in M of A. This subset is going to be called a Laurent domain. And what I want to claim is that there's a natural ring associated to this set, which, with respect to which is a nice universal mapping property. So let me first introduce the ring, and then we'll sort of see what the nice property is. So let me introduce the following ring that I'll write as, well, in longhand, you'd write it this way. In shorthand, you'd write it this way. So the definition is the following. So you think about in this generalized Tate algebra construction, what you're always doing is you're throwing in things and you're sort of forcing them to be somehow norm less or equal 1. Okay, that's sort of the property of the variables in a Tate algebra. So what I want to imagine doing here is I want to, in some sense, create the universal capital A algebra in which the first n elements are bounded by 1 in norm, and the last m elements should be units whose reciprocals are bounded above by 1 in norm. So what I should do is form the Tate algebra in n plus m variables, and I'm going to mod out by these relations and these relations. It's just a construction. Okay? There it is. What I want to claim, so this is an A algebra. It's aphanoid, because A is aphanoid. What I claim is that the max spec of this, mapping back to the max spec of A, goes bijectively onto this set. And in a certain sense, this can be characterized by a universal property in relation to this set. So let me formulate the universal property of this construct. But the important thing, again, the simplest example of all, A bracket little a would just be A bracket x mod x minus a. This is this thing I screwed up in the last talk. Okay? This in general is not actually the ring capital A again. Roughly speaking, the max spec of this is going to be the subset of M of A, where this guy actually has absolute value less or equal to 1. So it's a little piece of the whole space. If this guy does have absolute value less or equal to 1 everywhere, this is, in fact, the same as capital A. In general, it's kind of a ring associated to a smaller set. So in order to make that precise, let's see what the universal mapping property is. Unfortunately, now I have to take that piece of paper off, so now you've all forgotten it. So let's write it up again. So what's the property? What's the universal property of this ring? Well, let's consider, let me give this thing a name. For now, let me just call this set U. These guys will be fixed. Okay? So we have the subset U in here, and now I want to this is, in fact, an open set for the canonical topology. That's hardly a surprise. These kinds of inequalities, if you think on the level of geometric points, is kind of an open condition, right? We're in non-Archimedean land. So this is an open set for the canonical topology. But I want to claim that this set determines this ring in a very natural way. So what's the universal property? Well, let's consider any map to a k-aphanoid. Of course, my maps are always understood to be k-algebra maps. All right? Such that M of B to M of A factors through that subset U. And this is the subset given by the conditions AI less or equal to 1, AJ prime greater or equal to 1. Okay? So suppose that actually factors through this set. This is just a set theoretic property of the max spec map induced by this map of rings, map of k-algebras. Then I claim, such that this happens, I claim this condition that it factors through this. This is equivalent to the property So I claim the property that this factors through this set is logically equivalent to the condition that it actually factors through this map, and that, in fact, such a factorization is necessarily unique. Okay? And the analog to keep in mind is when you're working with a scheme, spec A, and you have an open subscheme, spec C, that if you have a map to any ring whose spec map set theoretically factors through, that's logically equivalent to factoring through it in the sense of schemes, because it's an open subscheme, and therefore it's equivalent to uniquely factoring through that open subscheme coordinate, that open affine subscheme coordinate ring. So the fact that an algebra may be characterized by a set theoretic mapping property is in fact something that's familiar from algebraic geometry if you think about the case of an open affine subscheme of an affine scheme. Right? And this is going to be the same thing here. So why is this the case? Well, set theoretically, what this condition says is if you take these elements AI and A and you pull them back to here, if you view them in B, they're pointwise less or equal to 1. They're power bounded, which exactly says that there's a map from a generalized Tate algebra to here, which carries the variables to these. And if you look back at the definition, in this ring, we've exactly just set those Tate algebra variables to equal these elements. So that's the power boundedness condition. And similarly, this condition says that the elements A, J prime, when you view them in B, pointwise, they never vanish. In fact, they have absolute value greater or equal to 1. But in particular, they never vanish at any maximal ideals, and therefore the AJ primes must be units in here. Being units, the reciprocals are pointwise less or equal to 1, which turns out to correspond to the other condition in the definition. Anyway, so this is sort of an exercise in the notes. Okay? But again, the analog to keep in mind is if you have spec C is an open subscheme of spec A, and you have spec B mapping to here, and you have this guy set theoretically. If you have the map which set theoretically factors through, then it even factors through as schemes. But we don't have schemes here. We don't have geometric space. We have rings, i.e. the set theoretic condition is equivalent to saying that the algebra map A to B factors uniquely through the map A to C. Okay? So that's the universal, this is the universal property. Okay? In particular, taking B equal to this ring, we see a point in M of A is just a map to a finite extension field. So one consequence of this is that, in fact, M of this ring literally is U inside M of A. Because a point of this space is, up to Galois conjugacy, a map from this to a field. So you take B to vary through all finite extensions of K, then in fact you'll find that the points of M of A that live in U are exactly the points that come from here. And you find that this is in fact a bijection. Okay? So to summarize, this A algebra, its max spec space goes bijectively to U, and in fact any other space over A, or algebraically any other aphanoid A algebra, whose max spec space factors through it set theoretically, in fact factors through it ring theoretically in the opposite direction. Okay? So this subset is called a Laurent domain, and we see by this universal property, so because of the universal property, U, the subset, determines this algebra as an A algebra. Okay? It's determined by the universal property. So let me record that. So the upshot is, so the Laurent domain U in M of A determines the A algebra, which I'm now going to call A sub U, up to unique isomorphism. Okay? And this will become the coordinate ring associated to this subset. But I just want to emphasize that it is functorially associated to the subset by means of that universal mapping property. Okay? Formulated purely in terms of this sort of algebraic language. And I should mention two remarks along these lines. First of all, if there are no A primes, if you only have this, i.e., if U is just cut out by a bunch of conditions AI less or equal 1, this is called, this algebra is called a Warshaw's algebra. Well, the domain is the set. Yeah, so anyway, for this guy, we say that U is a Weierstrass domain. So this is a special case of Laurent domains. Now, of course, some of you are wondering, why do we call them Laurent domains? I'm wondering why they're called Weierstrass domains, but we'll come to that in the question session. We'll see in a moment why they're called, I think, why they're called Laurent domains. Anyway, when we're just imposing upper bounds, we get no denominator stuff going on. This has a special name. Actually, I think I know the reason for that now, too. But anyway, the other property that's very important to record is you might think, why are we only imposing absolute value less or equal 1? Why don't we impose absolute values with other real numbers instead? And so this is a very important remark, which will come back to haunt us later, that in fact, let me write, so radical absolute K star. This is the so-called divisible group generated by the value group. These are all the positive real numbers, some power of which is the absolute value of something in the field. Okay, this is a divisible group. For example, if K is, so let me just say, for absolute K, so for example, if K is QP, this guy, these are the rational powers of P, assuming I use the usual p-adic absolute value. Anyway, so if I consider this sort of divisible value group, notice that if I give you any epsilon in here, and I consider an inequality, let's say f less than or equal, or f of x less, the condition f of x less or equal epsilon, this is equivalent to the condition f to the n of x less or equal epsilon to the n. So if we choose n, so this is the absolute value of something in the field, then this is equivalent to the condition that C inverse f to the n of x is less or equal 1. Okay? So to the extent we're going to put in inequalities on values of functions involving real numbers in the kind of divisible group, the surd, whatever, of the value group, it's no more general than just considering absolute values, upper and lower bounds on values of functions with 1. Okay? So you could put in superficial generality into the definition of Weierstrass and Laurent domains by allowing more general numbers on one side of the inequality, but in fact, it's no different than this, provided we change the function. Okay? So we have slightly more flexible range of inequalities that we can consider. In fact, for example, I guess let's come to the example of the, so let's look at an example. Let's take the ring, let's just take the Tate algebra in one variable. And let's think about the condition absolute x less or equal, 1 over the square root of p. Okay? This is equivalent to the condition that I always get, okay, so let's just do it slowly. X squared less or equal 1 over p is the absolute value of p. So this is p inverse x squared less or equal 1. Okay, if I got that right. And so what we see is that this locus sort of points in m of kx. Oh, x. So points xi in m of kx with coordinate, coordinate meaning x of xi less or equal. If I impose the condition to be less than or equal 1 over root p, this is in fact this is a Weierstrass domain, and this is cut out by the condition. Well, this is a of this element x squared over p. Okay, so we see if the closed unit disk, the closed disk of radius 1 over square root p is a viable. It is in fact a Weierstrass domain, all right? And there's its coordinate ring. Okay, so we can allow radii that are arbitrarily rational powers of p. We can't allow all real powers of p yet. Well, not going outside the unit disk. But anyway, so we can have, in fact, quite a wide range of radii that we can consider already with this kind of condition. Let's look at another example. So let's take the condition. Now let's choose a better variable name. So we'll take a to be k bracket t. Let's look at and let's pick an element in k whose absolute value is between 0 and 1. And let's consider the condition that sort of absolute value of the coordinate is between 1 and 2. So consider this locus inside of m of a. All right, inside the closed unit disk in this sort of Tate sense, let's consider the condition that we impose on the coordinate that its value, kind of an annulus. This is, you think of it as like an annulus. Right, something like that. Right, center is somewhere in there. Well, center is everywhere. Anyway, so we have this annulus, and what does this correspond to in terms of the rings? Well, you can work this out for yourself. I'll just say if you see exercise 2.16, just for purposes of time, I'll just tell you the final answer. If you call this u, you find that a of u is just, well, it's not actually a surprise once I write it down. I mean, if you trace through these Tate algebra definitions I gave, you'll eventually find you get this. And what is this saying? It's saying you throw in an extra coordinate to force c over t to also be less or equal 1. And that, right, this thing just exactly says c over t should be less or equal 1 as well. And that's exactly what this ring accomplishes. Okay? So this ring is, in some sense, going to be the coordinate ring of this annulus. Okay. Anyway, so those are the Weierstrass and Laurent domains. And so that's one class of open subsets for the canonical topology that are going to be quite interesting for us. But we want to consider another kind of subset. And this will be the rational domains. So here, there's a little bit of a wrinkle. I consider some elements in my coordinate ring and another element with no common 0. All right? Of course, to have no 0 means to not lie in any maximal ideal, which means they generate the unit ideal in the ring. Okay? So suppose I consider a bunch of elements, and now what I'm going to consider is the condition that absolute A1 less or equal absolute A prime for all I inside M of A. Okay? So we're going to consider all points where AI of x has absolute value bounded above by A prime of x. All right? And this also has a corresponding coordinate ring. So let me just define A sub u in this case. It's usually denoted sort of A1 over A prime, AN over A prime. And what it is, the actual definition is we throw in some variables. And we want the variables to be these fractions. So we mod out by the relations A prime xi minus AI. Okay? And if we do that, then one can check there's a universal property that if I give you any map A to B, then this map factors through U if and only if it factors through this what I've called the coordinate ring. Okay? So this is a class of conditions where I'm now having an inequality, but now I have functions on both sides of the inequality. Before I had a number on one side or the other side. Now there are functions on both sides. For example, it could be just two functions with no common zero, and then you impose this condition. You could consider this without the condition of the common zero, but then in fact the universal property doesn't work, and this is not even an open set for the canonical topology, so it's probably a bad thing to consider anyway. In any event, so this is another construction, another class of inequalities we can impose, and this in fact is also the condition of factoring through this kind of set is in fact characterized algebraically by factoring through this particular ring. Okay? And these subsets are called rational domains. Right? And so we'll see some nice properties that these things have a little bit later. Okay, so these are these Weierstrass domains and Laurent domains and rational domains are, in some sense, the fundamental kinds of open. These are all open for the canonical topology. This is an exercise in the notes. And these are the fundamental building blocks from which we're going to create the general notion of what should be like an open affine subscheme. Okay? So to do that, let's now, motivated by those examples, let's now define what should be the analog of an open affine subscheme, even though we don't yet have a structure sheaf. So definition, an affinoid and I should say, and I'll be corrected by someone in the audience if this is mistaken, that when this theory was first created, I believe that pretty much these were the only building blocks that were used, and it was only later that the following definition that I'm about to give was sort of identified as a workable notion with respect to which certain aspects at the beginning of the theory become much easier to manage. Rather than just working with these three kinds of examples, we have the following general notion, which a priori will seem completely unworkable. An affinoid subdomain U in M of A is again always affinoid, is a subset such that there exists a map to a k-affinoid algebra with the universal property for factoring in the sense of the previous examples, that any A to B phi has M of phi, the pullback map, factoring through this subset if and only if the algebra map factors through, and in which case I demand the factorization be unique as well. Okay? So examples of these things are the things we just saw. Weierstrass, Laurent, and rational domains. For those three kinds of subsets, we constructed an explicit A sub U so that there was this property. And let me emphasize that in this universal property, U is only intervening as a set, but the other side of the universal property involves this A algebra. Okay? So this really does functorially determine this ring from this set. Notice it's not part of this definition that this is open for the canonical topology, but in fact, it turns out it is open for the canonical topology. In fact, there's a very fundamental result, which I'm just going to state, but you can't appreciate how, I mean, this is not at all an easy thing to prove. So there's this theorem due to Gerritsen and Grauert, which says that, in fact, every affinoid subdomain is a finite union of rational domains. This is a remarkable fact. Now, the way you should think about it is the rational Laurent and Weierstrass domains are the analogs of like basic open affines, whereas affinoid subdomain is more like the notion of just an open affine subscheme. And it's very nice to have the general notion, but of course, in general, in algebraic geometry, it's hard to tell, first of all, when a given finite union of open affines, basic open affines, is again affine. So there's not really any kind of converse to this theorem. This theorem is more saying that affinoid subdomains are something you can really work with. But at the same time, having these guys as the basic building blocks will be very useful for doing calculations. Okay, so this is a remarkable fact. But the affinoid subdomain is in some sense the more fundamental notion. Okay, as an example of the universal property of affinoid subdomains, to the extent that these things exist, and we certainly have these Weierstrass, Laurent, and rational examples, if I give you an inclusion of affinoid subdomains, well, then first of all, I should have remarked from the universal property, sorry, let me just come back to here for 1 second. Affinoid? No, not at all. Not at all. Yeah, so there's no converse to this theorem. Okay, I'm just saying any one of these is of this type. A particular example of this, again, if I take B to vary through finite extensions of K, then in fact you find that actually M of AU goes bijectively onto U. Okay? So this coordinate ring, its max spec space literally is U, just like in those 3 basic examples that we had. So now if I give you affinoid subdomains, well, this guy is M of AV, and this guy is M of AU. So since this map corresponds to A goes to A sub U, and it factors through this, we get by the universal property of V, we get a natural map that the map A to AV, A to AU, that there's a unique map. Maybe you call it restriction from U to V. Right? Call this map maybe A goes to A restricted to V. Whoops, let's try A restricted to U. Okay? So it's just notation. So anyway, given an inclusion of affinoid domains, we get a natural map in the other direction between the corresponding coordinate rings. This is very suggestive that we should be able to put these together into some kind of sheaf. Okay? So we're sort of starting to make progress towards giving these spaces some kind of reasonable algebra geometric structure. So before we sort of move further in that direction, I should just mention in the context of these subdomains, you might want to talk about intersecting. An intersection of affinoid subdomains should again be an affinoid subdomain, but what should the coordinate ring be? If we were in algebraic geometry, the coordinate ring would be the tensor product, the fiber product over the base space. It would be the tensor product of the 2 coordinate rings over the ambient coordinate ring. So we haven't discussed tensor products. Now let me just mention it briefly. So remark, I mean, it'll be a long story to discuss, but you'll certainly find it eminently plausible that there's a good theory of completed tensor products. So if I give you A, B, C maps of K affinoids, then there's a good theory. It's developed in the exercise in the affinoid case. You can even do this for Banach algebras. There's a good theory of the completed tensor product, and it will correspond to fiber products in our situation. This implies that if U and U prime and M of A are affinoid subdomains, this is characterized by a universal property of the type that's not surprising. If these are affinoid subdomains, then so is the intersection using AU completed tensor over AU prime as coordinate ring. It's just a simple matter of unwinding the universal properties of everything in sight. That's remark number 1. And remark number 2 is I'll just say likewise for extension of the base field. Okay? There's an operation of completed tensor product against a field extension. And again, if you have an affinoid subdomain and you apply it to both the ambient ring and the subring, that you again will get something that's an affinoid subdomain in an appropriate sense. Anyway, so these are the affinoid subdomains. And just from that alone, we already start to get something reminiscent of the sense of a structure sheaf. And so now we can finally introduce the definition that gets the whole theory off the ground, which is the class of open sets that we're going to allow ourselves to consider. So let's let A be a K-affinoid algebra. And I'll say that a subset U in M of A is admissible. Well, if what? I want it to have a covering by affinoid domains. Now, if I just took unions of affinoid subdomains, that would be useless because I just recovered the canonical topology. I want it to have a covering by affinoid domains with the universal property that whenever I have another affinoid space mapping in, that the pullback has a finite subcover. I want to basically introduce a definition that will force affinoid spaces to be compact, or to behave as if they were compact. If there exists an affinoid covering by affinoid subdomains, UI of U, so these are affinoid subdomains, such that now you have this weird mapping property. It involves all possible maps from all K affinoid algebras to A. So it sounds very unworkable. From A to anything. all k-aphanoid algebra maps A to B such that M of B lands inside U, okay? The pullback, let me call this map psi. This psi of Ui, this is a covering of M of B. This has a finite aphanoid refinement. Aphanoid subdomain refinement cover in M of B. Okay? So I pull back, or in fact, it's much more concrete. This just has a finite subcover because these are aphanoid domains in M of A. This is coming from a ring map. So if I just use a completed tensor product, this preimage, so in fact, let me just mention, psi of AUI is in fact just M of B completed tensor over A, AUI. All right? So you could either say refinement or subcover. All right? So you have an aphanoid covering so that under the pullback from any map to another aphanoid, in fact, the pullback cover has a finite subcover. Right? That's the definition of an admissible open subset. All right? And as an example of an admissible open subset, I leave this as an exercise. If I take A equals the Tate algebra in one variable, and you take U to be the set consisting of the condition absolute value less than 1, and you take Ui to be the condition absolute x less or equal absolute c to the 1 over I, where c is something with absolute value between 0 and 1. These are Weierstrass domains. Set theoretically, they cover U. And I'll leave it for you to check. The maximum modulus principle is the content of this condition. I'll just tell you, any aphanoid mapping from here, which lands in here, says that the pullback of x to the other ring is a function on an aphanoid algebra that's pointwise less than 1 in absolute value. So by the maximum modulus, it's bounded away from 1, which actually says that the map lands inside one of these pieces. Okay? So this is the sort of fundamental example of an admissible open set. And now let me tell you about the coverings that we're going to consider. So another definition is an admissible cover. Let's let U in M of A be an admissible open. All right? And a set theoretic cover of U by other admissible opens, Ui, is called admissible if what? Well, again, we're going to use kind of a test object criterion. Again, for any map of k aphanoids such that M of B lands inside U. All right, let me call this map psi. And now we impose this condition that psi of Ui can be refined, has a finite aphanoid. When I say aphanoid cover, I mean by aphanoid subdomains. Has a finite aphanoid refinement cover. Okay? So we have this notion of admissible opens, and we have the notion of when an admissible cover by admissible opens is admissible. And now let me give the fundamental non-example of this, which is, let's take the unit disk, and let's take U to be the condition absolute x less than 1, and take V to be the condition absolute x equals 1. Yes? No. Right. I should say, one should check, and I think it's an exercise in the notes, that under a map of aphanoids, the preimage of an admissible open is always an admissible open. So in fact, these guys are actually admissible opens in here. Okay? So I look at the so-called open unit disk, the boundary, so to speak. This is a set theoretic covering of M of A. This is all happening inside M of A. And the point is that this guy is not an admissible cover. So this is an exercise in the notes. So that, in some sense, suggests we're really going to get around this total disconnectedness problem. Okay? So we're going to restrict the class of open sets. We're going to restrict the class of open covers. And I'll just say the last definition is that the Tate topology on M of A is exactly, well, it's a very mild kind of what's called Grothendieck topology. For those of you who don't know what Grothendieck topologies are, you just don't allow unions, roughly speaking. We're going to consider, yeah, so I don't want to get into this, all this formalism. Let me just say that this is the data of the admissible opens and their admissible covers. This satisfies something slightly weaker than the usual properties of open sets and covers in topology, but it does have enough of the features, behavior under finite intersections, transitivity relations, and so forth, that it will provide enough to get a viable sheaf theory, to do sheaf cohomology, and other things. Okay? But this is where basically restricting the collections of opens and coverings of opens that we consider. Okay, so that's the notion of the Tate topology, and the fundamental theorem that gets the whole subject off the ground is the so-called Tate acyclicity theorem, which says the following, that if A is k-aphenoid, then the assignment U goes to A sub U for aphenoid subdomains U and M of A, I'll just say satisfies the sheaf axioms for finite covers of one aphenoid by others. Okay? In fact, he says much more. It says that if UI is such a cover, meaning a cover of one aphenoid subdomain by finitely many others, then if you make the check complex, starting off with well, A sub U, going to the product of the AUIs by restrictions, going to the products of on the overlaps. These are, again, aphenoid by taking successive differences, and you have triples of differences, and so forth, that this is an exact sequence. The proof of this is absolutely brilliant. You manage to eventually, cleverly, by using abstract check methods, you reduce yourself to a very concrete calculation with a pair of, with a Laurent covering. It's discussed as an exercise in the notes. I don't have time to get into it here. Anyway, so this is the basic building block. This basically says that for the Tate topology, so the consequence of this is that there's a unique sheaf, I'll call it O on M of A, I'll call it O sub A on MA, with respect to the Tate topology, such that OA of U is A sub U for all aphenoid subdomains. U in M of A. Now, when I say sheaf, the important point is sheaf axioms I only consider for admissible opens and their admissible coverings by admissible opens. I don't try to talk about the covering of the disk by the open unit disk and the boundary. That's not an admissible cover, so I wouldn't talk about gluing with respect to that cover. All right, so I only use admissible opens and admissible coverings of them by others. And there's a unique way to promote this to a sheaf for that Grothendieck topology. Okay, so that said, now we can sort of try to globalize this notion. Let me just tack in the definition. The SP of A will be the space consisting of the pair M of A together with this sheaf for its Tate topology. Okay, this is a Grothendieck topologized space, whatever that means, together with this nice sheaf of rings that, at least on the aphenoid subdomains, is just given by the coordinate ring. Okay, so now I can tell you the global notion. So a rigid analytic space is a pair over K, is a pair XOX, where I'll just say X is what I'll call a G topologized space. Well, it's discussed a bit more fully in the notes. Roughly what this means is it's a space together with a specification of certain subsets that we call opens and a distinguished class of set theoretic coverings that we'll call their admissible coverings, much in the spirit of the aphenoid situation. In particular, it's weaker than the data of a topological space. All right? But it's some kind of distinguished collection of opens and distinguished coverings. And this should satisfy the sheaf axioms for that, such that it is locally, in the sense that there's an admissible covering of the space by opens, so that the restricted data on that open is isomorphic to SP of an aphanoid. And isomorphism, I'll just say with respect to the evident notion of morphism, and what I mean by that is the following. It's like the definition of ring spaces. If I have two such pairs, a map between them is a map of these sets which pulls back distinguished opens to distinguished opens and distinguished covers of such to distinguished covers, so it's sort of continuous, and a map on sheaves in the opposite direction, just like in the sense of ring spaces, such that a stalk condition holds to make it locally ringed. Okay? So this is a nice analog of locally ringed spaces, and they should be locally coming out of aphanoid spaces. And a fundamental fact that gives this theory its substance is given any map of aphanoids, you get a map between the corresponding spaces. This is called an aphanoid space. And this is a fully faithful functor, meaning, just like in the case of spec of a ring, that any map between the associated spaces in this sense, in fact, arises from a unique map of aphanoids. You basically just take the proof for spec of a ring and you copy it by changing a few words here and there. Okay? So this is sort of a global notion, and the thing I should emphasize, although we don't have time to get into it, is you really can you develop a theory of gluing, so you can create fiber products by gluing in the aphanoid case using completed tensor products. You can glue a rising family of disks and make what you would call a rigid analytic affine space, and then you can cut out pieces of that. You can analytify algebraic schemes to these rigid spaces, just like you do over C. We're given an algebraic variety. You make some kind of complex analytic space. And then you can contemplate analogs of the Gaga theorems and so forth. And let me just end with one last crucial example. We'll discuss coherent sheaves in the third lecture that I'll give. But one last example I'll say is, we'll say that XOX is disconnected if there exists an admissible cover UV by admissible opens in the sense of this G topology, such that, well, of course, they're disjoint and they're non-empty. I know there's at least one person in the audience who's going to disagree with this definition, but we'll take it outside afterwards. Anyway, so that's just the definition of disconnected. You call that a separation. And the interesting thing is, so theorem, that XOX, if it's not disconnected, you call it connected. So the empty set is connected. Anyway, X is connected if and only if gamma XOX has no non-trivial idempotence. In particular, just like if it was a ring space, which it's not. In particular, if you look at the aphanoid case, the global function is just A, just from how the structure sheaf is defined. And so what that's saying is, if A has no non-trivial idempotence, like the Tate algebra, then there's no admissible separation, right? So for example, the closed unit disk is in fact connected from this point of view. Okay? So in this way, we see that by restricting the opens and the admissible and the coverings we consider, we've rescued the theory of connectedness. And the exercises explain there's a nice notion of connected components and so forth. Okay? So you have very nice analogs and quasi-compact maps and various other things that we're familiar from algebraic geometry. Okay? And so to go further, we need to discuss coherent sheaves, and we'll do that in the next lecture. Okay, I'll stop there.
Great. So are there any questions?
Okay, so the question was, does a variety over K determine a canonical associated rigid analytic space? So I kind of said this perhaps too quickly at the end. So the answer is yes, that if I give you any scheme locally of finite type over K, then you can associate a rigid analytic space to it, satisfying a universal mapping property, much like in this thing at the end of SGA1. But locally, basically, you make affine space and you glue things. And so there is a good theory of analytification which has properties very analogous to the case over the complex numbers. In particular, there's Gaga theorems, and you can copy Serre's proof, and so forth. We have to define properness to make sense of that, but that'll be later. You can make projective space. It has a universal property for a suitable line bundle that also requires coherent sheaves. So yeah, there's a very good theory of analytification. Yeah?
In algebraic geometry,
Varieties are always reduced.
Okay, if the scheme is
Yeah.
reduced, it's sort of very comforting to think, when you're thinking about localization, it's comforting to think in terms of the fraction field.
Is it? Yeah, okay. Yes, yes. The total ring of fractions. Right. Irreducible. Yeah, yeah, yeah. I understand. Yeah, yeah, yeah. So you have a function field. So do these things have function fields? Is it? No. Right. Right. So this localization process, this is an important point. It's much more drastic than an algebraic geometry. So if you have an aphanoid and you have an aphanoid subdomain, the coordinate ring on it, it's in some sense very big over the ring. You haven't just inverted. You sort of like inverted and completed in some sense. So the closest relation you can say is that for any point in the subdomain, the stalks of the structure, the completed local rings of A and A sub u are in fact the same. So you can't say that, for example, they have the same algebraic local rings at a common maximal ideal point. But they do have the same completed local rings. So there are some, you can make some relations between them, but you usually have to go through the completion. You can't, the operation is much more drastic than algebraic localization. And in particular, the working with, for global objects, you don't really have anything quite like a function field. Yeah. I mean, working algebraically with the, okay, now Michael's going to point out this is not quite true. Yeah. Oh yes, this is a very good point. The theory, so in algebraic geometry, irreducible components are, the theory of irreducibility is sort of a very straightforward operation. But this localization is much more drastic. It's much like an analytic geometry. You can have an analytic space, which is not a union of two proper analytic subsets. But of course, if you work local, if I had a blackboard, oh wait, I do. Right? I mean, you have the analog of this. Right? And so things can break apart. And so you should really think that the properties are more analogous to complex analytic. It's this weird hybrid that the spaces are built out of rings, but they're kind of more complex analytic in behavior. So it's funny somehow. Yeah.
All right, well, that's very good. The next talk is at 11:30.
Is that notion of rigid